Hello everyone, welcome to the four live session of NPTEL's Introduction to Semiconductor Devices course. I'm Om and today we will be discussing some questions that will help you with your uh, exams as well as your assignments. So let us start. In this week, we'll mainly look at some introduction of the PN junction electrostatics, fixed charge, free charge, depletion approximation, electric field, built-in potential, and different kinds of junctions as well as the bend diagrams. So before going to the questions, let's have a quick recap of the course slides. So this is your lecture material from the course. So I hope you all have watched the lectures. If not, I suggest you to please watch the lectures and then solve the assignment. Then it will be very easy for you to understand it. So in PN junction electrostatics, consider a step graded PN junction at thermal equilibrium where P side dopant is Na. So we have a step graded PN junction where P side is Na and N side is Nd. Diffusion charge carrier creates a depletion region which is formed across the junction with W. So electrons move from here and holes move from here. It forms a depletion region. It's called a WD. And the depletion region on the P side is XP and N side is XN. Here it's XP, here it's XN. Due to the net space charge density, there is an electric field exists in the depletion region. So since here you would have positive charge, here negative charge, so there will be a net electric field in the depletion region. Its direction is from N to P, as shown here, from N to P. The maximum field E max is created exactly at the junction, so exactly at this middle junction, the electric field will be highest. A potential difference known as the built-in potential is formed across the region. So due to this electric field, there is a potential difference here between this point and this point across the junction, and this potential difference is VBL, built-in potential. At equilibrium condition, the electric field is continuous at the junction at x equals to 0. This is x. So at x equals to 0, the electric field is continuous. And we have the charge neutrality condition. This NAXP is equals to NDXN. And the maximum electric field is given by QNA by epsilon XP equals to QND by epsilon XN. This is the maximum electric field. And the built-in potential across the junction is minus Q by 2 epsilon NDXN square plus NAXP square, which you can also derive as VBI equals to KT by Q and then NAND by NXP. The width of the depletion region W is given by 2 epsilon Si by Q, 1 by Na plus 1 by Nd into VBI. And the width on the P side is Nd by Na plus Nd into W, and at N side is Na by Na plus Nd into W. So consider a one-sided junction. A one-sided junction would be something like P and N, but there is doping is Na, here doping is Nd, and much greater than Na. So most of the depletion region will be formed on the P side and very less depletion will be formed on the N side. This is called a one-sided junction. Such as Nd is greater than Na, the depletion width on the N side is so small that the Entire depletion width is almost equal to, so this entire depletion width is almost equal to xp, which is the coordinate of the x side of the depletion. The depletion region will cover almost the in the lightly doped region Na. Similarly, for P plus N junction, Na is greater than Nd and W is equals to Xn. In absorb junction, W is proportional to square root of VBI. In linearly graded junction, W is proportional to cube root of VBI. And this is just example of different PN junction profiles and their charge density plots and their electric field plots. So in a normal step abrupt PN junction, here this is P side, this is N side, this is the charge density profile. Here is positive charge, here it is negative charge, and the electric field that you come up with is like this. Electric field will flow from N to P, that is opposite to the direction of X. That's why it is negative. In a linearly graded, that means your doping is changing something like this. It's zero here and increasing, zero here and increasing. That's why you get this kind of charge density profile, which is zero at the center and increasing with X. So for this linear curve, you get a quadratic charge profile. Again negative because charge flow opposite to because the electric field is opposite to the direction of X. The PIN diode, I is the intrinsic region, so that space charges only in N side and P side. There is no charge here. So this is the charge diagrams. So again, electric field will increase, then stay constant since there is no charge change here, then again come to zero here. In an abrupt side, it will increase very rapidly in the negative side and fall very rapidly on the positive side. Increase slowly on the negative side and fall very rapidly in the positive side. This is here. Uh, it is an abrupt junction and there is very high and very high ND. So just we'll look at a few slides also. So this is about the depletion region of the space charge. So the depletion approximation basically means like in this region there are only fixed charges, no electrons or holes. These are only donor atoms and acceptor atoms. No ionized donor and acceptor atoms, no electrons and holes. So these are uh, free charges are removed from this region. So this is the depletion approximation. And to find the electrostatics, we start with the Poisson's equation. This is the Poisson's equation. This comes from the Gauss law. So Poisson's equation is del 2V equals to minus rho by epsilon, or we can write it as dE by dx equals to rho by epsilon. And we replace rho. So here this is the charge plot. This plus minus minus xp plus xn. This is 0. This is qn. This is qn. So electric field key comes out to be, if we integrate this, qn dx by epsilon n plus c. And the electric field is like this. This is the correct electric field. E is negative because electric field will be from positive to negative direction. So this is just the derivation of electric field. So to solve it, we get this is the electric field and this is on this side and this is on this side. Electric field is continuous at x equals to 0, which gives us a charge neutrality condition. And dxn equals to NaXp. And if we integrate the electric field, what we get is the potential V is minus E dx. So we just find the area under this curve, half into base into height. So this gives us the VBI, the built-in potential. And the depletion width we can also find like this. We know NAXP is NDXN. So W is XP plus XN. So substituting it here, XP is this, XN is this. In electric field equation, we can substitute this. And in VBI, we will get finally W is under root 2 epsilon by Q Na plus Nd into VBI upon Na. This is the electric field. Okay, so this was just a brief overview. So this is nothing. You have already read all these in the lecture videos. This was just a recap that will help you with your assignment. So we can start now. So at any time, if you have any doubts, please feel free to unmute yourself and you can ask the questions, or you can also type it in the chat box. Okay, so according to the depletion approximation, what primarily constitutes in the electric field in the depletion region? A. Free electrons and holes. B. Neutral atoms. C. Ionized dopant atoms. D. Both free carriers and dopant atoms. Right, it is ionized dopant atoms. Right, because we saw the depletion approximation. So free carriers are electrons and holes. Free carriers or mobile carriers, right? Because they can move. That's why they are called free or mobile. Then we have immobile or ionized atoms. These are your donor and or acceptor ionized atoms, which have already given an electron and hole, and now they are just fixed, act as a fixed charge. So in the depletion region, what we have is in the N side and P side. In the N side, we have these positive ions, and P side we have these negative ions. Positive ions are because the donor atoms have given one electron and now they are positive. Acceptor atoms have taken one electron and now they are negative. So this is the depletion region where we have ionized dopant atoms. Okay, next question. Consider a PN junction where the difference in doping on both, where there is difference in doping on the both sides. Then the space charge region will be extended more into which region? Lightly doped, heavily doped, middle of the junction, cannot determine. Okay, right? The answer is likely to. So if we have a PN junction, it's Na and Na much less than Nd, then most of the depletion will be formed here. Very less depletion will be formed here. Depletion extends more in the lightly doped side. And this can be shown with charge neutrality also. NaXP equals to NdXn. So to maintain both of these quantities equal, since Nd is much higher, Xn will be much lower, right? So most of the depletion will be on P side for this case. That is the lightly doped side. Okay, next question. For the next two questions, question 2 and 3, consider an abrupt PN N plus junction with doping profile as shown in the figure below. Based on the doping profile, answer the following questions. Okay, so we have an abrupt junction again where we have N is much less than Nd. Now the question is identify the corresponding charge configuration of the P-N plus junction. So for this junction, we have to draw the charge density diagram, rho versus x. So which of these is the answer? So answer to this is option A. Okay. So the answer to this part is option A, right? Because we just saw here the charge extends to a larger extent and here it is very small. So the option A. Okay, next one. Identify the corresponding electric field profile at the P N plus junction from the figure given. So for this same junction and for this charge density plot, we have to make the E versus X curve. What should it be? Right, it should be A again. So just saw it. Here, this is the positive. Here, this is so electric field would also be like here it will increase, then decrease rapidly. There's no electric field in the quasi-neutral region. Electric field is zero. Electric field only exists in this region. This is how electric field will look like. And this is negative again because electric field is from positive to negative charges, and this is opposite to the direction of x. That's why it is negative. Right, next question. So for questions 4 and 5, the doping concentration in abrupt silicon PN junction at temperature 300 Kelvin are Na of 10 to the power 14 per centimeter cube and N of 10 to the power 18 per centimeter cube. Assume Ni of 10 to the power 10 per centimeter cube, KT by Q of 25 millivolt at 300 Kelvin is the epsilon Si and epsilon naught. Find the built-in voltage of the PN junction. Please try to solve this question. All right. Yeah, the answer is option C, zero point 0.7. So to find VT, sorry, VBI is KT by Q, ln NA and D by NI square. KT by Q is 25 millivolts, 0.025 ln N is 10 to the power 14, 10 is 10 to the power 18, and I is 10 to the power 10, 10 square. We solve this, we get 0.69. The progress is zero point 0.7. So this is the answer. A straightforward question. When we have a p-n junction, we use this relation to find UBI for a step abrupt p-n junction. Next question. What is the total depletion width of the p-n junction? I will write these values again here. KT by Q is 25 millivolt. T is 3 epsilon SI 11.9 epsilon naught is 8.854 into I minus 13 watt per centimeter square. N is 10 to the power 14 and is 10 to the power 16. 17 to the power 18 centimeter cube. We have to find the depletion rate WD. C is not correct. Please check your calculations again. Okay, so let's see this. So WD is 2 epsilon SI epsilon naught UBI by Q Na plus ND for ND. Substitute the values. 2 into 11.9 into 0.5 into 10 to the power minus 14 into zero point 0.7 on 1.6 into 10 to the power minus 19 and is 10 to the power 14 plus 10 to the power 18 upon 10 to the power 14 into 10 to the power 10 to the power 18 we can cancel with this entire term plus 10 to the power 14 is almost 0 compared to 10 to the power 18. So what we are left with is 2 into 0.9 8.85 on 1.6 into 10 to the power this is 5 by minus 19 so minus 9, right? This 14 minus 19 minus 5 minus 5 will go up and become minus 14 plus 5 is minus 9. You have 21 minus 9 here. And when we solve it, it comes out as 3 into 10 to the power minus 4 centimeter, which is equals to 3 micrometer. Answer is option B, 3 micrometer. Please check if you can identify a mistake, else if there is some point which is not clear, we can go over it again. Okay, see the next question then. Using the depletion approximation, charge configuration and field profiles are given for the PN abrupt junction, PN linear junction, and PIN junction in equilibrium conditions. We have to match with their corresponding electric field. We have to matching of the corresponding electric field with their corresponding space charge with their corresponding electric field plots. Let's see how to do this. We have already seen this in the recap of the course in the starting. It will be A will be this one, B is this one, and C this one. It is A3, B1, C. So for this, you just need to remember one thing, that d by dx is rho by epsilon. That means T is integration of rho, and in integration, a step when we integrate changes to linear, a linear on integration changes to quadratic, and 0 on integration changes to constant. So if you know this, then you can solve this question. Like we see, first step, it changes to linear. For linear, it changes to quadratic. And for the step 0 and step, it is like linear, then constant, then linear. Okay, next question. Consider a uniform p-type bar within which a thin sheet of positive charge has been embedded. So we have a uniform semiconductor of p-type everywhere the doping is again, but at the center of it we have embedded positive charge, a sheet of positive charge. The charge is fixed in the lattice and cannot move. This forces the majority carrier force to rearrange and satisfy Moissan's equation. Assume the sheet charge density Qp as shown in the figure. Which of the following represents the electric field? So we have to find the electric field profile for this. Okay, so let me just A, B, C. Okay, answer which one? B is simply for a normal NP junction, right? This is for a PN junction. This is for an NP junction. Here, there will be positive charge and negative charge. So charge will be like this. This is for a normal PN junction. Why will it be B? These two are definitely not right. Just think about the Poisson's equation. In which direction the electric field should be according to the charge, then answer. I don't know about that. Please think about it. Right, C is correct. So every junction that we have studied till now is an abrupt junction, right? It's not like this specifically is an abrupt junction. This junction is also an abrupt junction. Here we have P side, then suddenly N side. This is an abrupt junction. So in this one specifically, what we have special is we have everywhere it's P side, but in the middle there is positive charge. So its charge density would be something like everywhere at the bottom is negative, but here this is very small, very thin, positively charged, right? So if we make the electric field will go. So this is the x direction, this is the rho. So electric field, how will it be? It will go in this direction as well and this direction. So definitely electric field will be discontinuous now. So for this one, it will be negative to positive. Then from here, it will be positive to negative. Right? That's why it's option C. This we have seen in the class also. If you remember your notes, same question was taken by professor also in the lecture. So we have type doped semiconductor with positive charge in the middle. This is its space charge diagram, negative on both sides and positive in the middle. So electric field in this direction is negative, electric field in this direction is positive. That's why we have this. And there's a jump in electric field due to this fixed charge. Okay, next question. Find the magnitude of the electric field at the center of the depletion region of a silicon PN junction with Na equals to Nd equals to 10 to the power 15 atoms per centimeter cube. The built-in potential is 0.6 electron volt. Okay, so let's see how to solve this question. So it says we have a PN junction with some depletion field on both sides and both are equal. So we will have some electric field and some built-in potential, right? So this is the multiplication with W to the electric field, and this is what we get. So basically, the built-in potential VBI as we saw is the integration of E versus X curve, right? The area under this curve gives us VBI. This is W, and this is your Emax point. So VBI 1 by 2 into W into Emax, right? So your Emax should be 2 VBI by W. So if you solve this, we have VBI is KT by 2 ln NA NT by NI square, which is 0.026 ln. Sorry, VBI is 0.66 volts, and W depletion is under root 2 sin naught by 2 VBI and plus ND upon NA. So we have to do this, and if we do this, what we get Emax is 9500 volt per centimeter, which is 9.5 kilovolt per centimeter. VBI is 6.3 into 10 to the minus 5. How? Even if you calculate, I think KT by ln NA and D by NI square. Right? So it will be 0.025 or 0.026 ln 10 to the power 30, 10 to the power 20. So it will be zero point 0.6 only. How are you getting? Okay, W. Okay, I have not calculated W specifically. Okay, but after calculation, you will get somewhere near this. Okay, anyways, even if your calculation is not matching, that's okay. Just remember this concept. That's all you need to find the answer. So we already saw, right? The integration under this is VBI, and this VBI is actually half into base is W, height is Emax. So to find Emax, you will just rearrange this to get this. Okay, calculation is not important, but the concept is. So for this, the answer is option D. Okay, a few more questions. Let's see them. Consider, sorry, consider a silicon PN junction with uniform acceptor doping of 10 to the power 70 on P side and uniform donor concentration of 10 to the power 16 on the N side. No external voltage is applied to the diode. Assume Ni is 1.5 into 10 to the power 10 per centimeter cube. Epsilon and epsilon naught. The magnitude of the charge per unit junction area in the depletion region on the P side is. Okay, let us see how to solve this one. So what it says is Consider a silicon PN junction with uniform acceptor doping and uniform donor concentration. The external voltage is not applied. Assume Ni is there. The magnitude of charge per unit junction area in the depletion region on the P side. So what it's saying is you have a PN junction. So it's saying on the P side, what is the charge in this charge per unit area per centimeter square in this area on the P side, just on the P side depletion region. So to do that, what this, let's say this is WP, and let's say this is the total depletion rate. This should be W anyways. So W. So what will be the charge per unit area here? Call it QP will be WP into Q into NA, right? This would be the charge per unit area on the P side. Now to find this, we need to find WP. So WP will be just for it ND upon NA plus ND into W. This is the P side depletion with WP or XP. Now to find this, we need to find W, and W is under root 2 to epsilon SI epsilon naught upon Q VBI plus ND upon ND, and VBI will be KT by 2 ln NAND by NS, right? So we need to find everything starting from VBI to W, then W to WP, then WP to QP. This will be our final answer. So if we solve this, VBI is 0.026 and then 10 to the power 17 into 10 to the power 16 by 1.5 square into 10 to the power 20, which comes out to be around 0.75 volts. And W depletion will be under 2 epsilon SI into epsilon naught is 12 into 8.85 into 10 to the power minus 14 into 0.75 for 1.6 into 10 to the power minus 19, and is 10 to the power 17 plus 10 to the power 16 upon 17 into 10 to the power 16. This comes out to be around 0.34 micrometer. Now, depletion width on the P side will be ND upon NA plus ND into W. It will be 10 to the power 16 into 0.34 upon 16 plus 10 to the power 17. This comes out to be around 0.031 micrometer. Finally, the charge, that is what we want, WP into Q into NA. This is 0.031 into 10 to the power minus 4 centimeter into 1.6 into 10 to the power minus 19 coulomb into 10 to the power 17 centimeter cube, which comes out to be around 50 coulomb per centimeter square. Okay, why can't you take electric field equation? What equation in the electric field equation minus Q NA by epsilon XP plus X. This equation. Yeah, without plus it's okay. We can take this also, it's fine. But anyways, you need to calculate XP, right? And XP you can only find when you know W. This is what we have found here, right? This is XP only. W is same as XP. But at the end, what you need is what is the total charge on this side. That will always be this XP into Q into NA. This you cannot change. There's no other way to find this. So in between, you find VBI or W or whatever you want to find, either that's okay. But at the end, you need XP to calculate this charge on the P side. So what do we do with this E upon XP? We don't know the electric field. Right? Is it given? I don't think so. Okay, let's see this. E upon XP into Q is NA by epsilon. If you use this equation, I get 100. Okay. So how do we find E? Here I don't know. Here also I don't know XP also. The LHS equation is asked. I don't understand. What is asked is the charge on the P side, right? How this gives you that? Okay. What is V by Q? V by Q is energy. You have to find charge. Unit is coulomb per centimeter square. E is in volt per centimeter. XP is in centimeter. Q is in coulomb. This is giving me volt per coulomb. What do I do with this? Sorry, centimeter square coulomb. This one cancel. Volt per centimeter square coulomb. But what we need is coulomb per centimeter square, right? Okay, so yeah, so it is very important to understand like what is asked, right? We have to find what is the charge by this in the depletion region on the P side. That is simply cannot be anything else other than this. This is the width of the depletion region, XP or WP, into a charge of electron into the doping concentration there. Okay, so I hope this question is clear. We have one more question for today. A junction is made between P silicon with doping density Na1 is 10 to the power 15 and P silicon with doping Na2 is 10 to the power 17. Find the magnitude of the built-in potential. So now it's a different question. We have kind of a P plus junction, not Pn. So here doping is Na1, here doping is Na2, Na1 is 10 to the power 15 per centimeters cube, Na2 is 10 to the power 17 per centimeter cube. We have to find what is VBI. Now we cannot use here VBI is not equal to KT by Q ln V by NA square. This formula was only valid for the step junction, PN junction. This is not valid here. So how do we find VBI? So think where this comes from. Then you will be able to answer this. Where do we get this from? What is actually what does VBI actually mean? Then you will be able to answer this question. Okay, so let's see this. So in a PN junction, let's say we have a P side, this is N side, right? So if I draw the band diagram, this is how the band diagram looks like, right? This is basic level EF, right? This is EC, EF, EI, and E. So what is VBI? Simply VBI is this difference is 2 times VBI, right? In terms of band diagram, and this we can find like here also, right? This is QVBI, which is like sum of this and this as follows phi 1 and phi 2. So QVBI is phi 1 plus phi 2. And phi 1 is simply this is what EI minus EF, right, on the P side, which this will be KT by Q ln NA by NA, right? Where this comes from, we know that uh, n equals sorry p equals to li e to the power ei minus ef by at, right? So this gives us this phi 1 and this. Similarly, phi 2 will be kt by q, kt ln nd by ni. So VBI becomes phi 1 plus phi 2 is kt by q ln q. VBI becomes this. So VBI becomes kt by q ln na by ni square. This is how we get this formula, right, from the Venn diagram. Now, in our case, what we have is we have a p plus junction, right? Okay, so we have a p plus junction. Now I again draw the Venn diagram for this. So it will be again something like this. Uh, okay, so higher p side will be on top. It will be something like this. This is EA and this is EI, EC, EV. Now this is your QVBI, right? Which is also here. So this we can find by, let's say this is phi 1, this is phi 2. Now here QVBI will be QVBI phi 2 minus phi 1. So phi 2 will be KT ln Na2 by Na. Phi 1 will be KT ln Na1 by Na. Now EBI is KT by Q ln Na2 by Ni upon Na1 by Ni. Ni and Na will cancel. So VBI will be, take a new page. So VBI will be KT by Q ln Na2 by Na1. Okay. Here we have Na2 is the greater one and Na1. So now using this, we can find what is VBI, right? It is phi 2 minus phi 1 is VBI. Okay. So if we put the values, so KT by 2 0.026 ln 10 to the power 17 by 10 to the power 58. This will give us VBI equals to 0.121, which is option A. Is this clear? Okay, so these are all the questions I had for today. If there are no doubts, we can end the session. Okay, so band diagram is simple. So we've seen this before also, right? Let's say we have a PN junction. So here doping is Na, here doping is Nd. So in the band diagram, let's first draw EF, right? EF. So Fermi level in equilibrium is constant line. Now in P side, if doping is Na, then EF is closer to EV. And in N side, when we have doping Nd, EF is closer to EC, right? So in P side, EF is closer to EV, so this must be EV here, and in N side, it's closer to EC. So let's say EC. So this I have drawn. Now I just draw the rest part. So EG is fixed. I'll add EG. So I'll get this EC here. Here I'll add EG. So I get this EV here. Now I just connect it. This is how I draw for a PN junction. So we just need to remember this. EF is closer to EV in P side, and in N side, EF is closer to EC. Now for that P plus part, P plus junction, it's also simple, right? So first I'll draw EF is constant. Now here this is also P, this is also P, but this P plus is more P. So this will be P plus, side will be EV more closer to EF, right? Compared to this side. So here EV will be very close. Let's say EV is here. Here EV will still be close, but comparatively lesser, right? Here let's say this is EV on the P side. This P plus side, this is P side. Now I'll just add EG. Let's say EC, add EG. This will be EC here. Now this becomes like this. This is the band diagram for P plus junction. Okay. Okay. Anything else? Okay then. If there are no more doubts, we can close this session. Thank you all for joining. We'll see you again next week at the same time. So timing now is uh, Monday, 5 to 7 p.m. Earlier it was Sunday, but now it's changed to Monday. Sunday we will not. Okay. Please remember this. Anyways, you will get like you get a reminder 1 day before. So please be mindful to your emails. Okay. All right. Bye everyone. See you next week.